Hey, this is Precalc 2-3. We're going to be comparing the graphs of polynomials in its leading term, applying polynomial theory. Zeros of polynomial functions will be explored, and that's a review topic. Sketching the graph of a factored polynomial using the idea of multiplicities, intermediate value theorem, and then we'll be looking at some modeling. So let's get going. We did this yesterday, looking at example 3 here, comparing the graphs of polynomials and its leading terms. We superimpose the graphs of f of x, x to the third, minus x, 4x squared, minus 5x, minus 3, and along with the function g of x equals x cubed. Now, if you superimpose these on the same graph in successively larger viewing windows, a process called zoom out, and we did that yesterday. Continue zooming out until the graph look nearly identical. What do you notice? And here's the thing that we yesterday was about towards the end of class. Both odd degree graphs have similar end behaviors. Okay, so as you're looking at this, the limit of the f of x term as x approaches negative infinity and the limit of the g of x term as x approaches infinity is negative infinity. And the limit of f of x as x approaches infinity, and the limit of g of x as x approaches infinity is infinity. So keep in mind the end behavior for both graphs is the same, and we're trying to drive the idea that that end behavior is determined by the leading coefficient and that power. Now, in sufficiently large windows, the graph of a polynomial and the graph of the leading term appear to be identical. The leading term dominates the behavior of the polynomial absolute value of x as it approaches infinity. Now, the leading term test for polynomial end behavior. For any polynomial function, f of x, a sub n x to the n plus dot 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 plus a1x plus a naught, which is, by the way, the y-intercept when x is 0. The limit of f of x as x approaches infinity and the limit of f of x as x approaches negative infinity are determined by the degree n of the polynomial and its leading coefficient, a to the n, a sub n, excuse me. So as you look at this over, it's exactly what we talked about yesterday, as the limit, of f of x, approaches negative infinity goes to negative infinity, and the limit of f of x as x approaches infinity is positive infinity for any n being odd. So if I have x to the odd power, any odd power, okay, for x, and when I have an even power for x, when it's positive, I have both limits going positive because on even powers are either both up or both down. Now when I have a negative value, negative leading coefficient, these are both positive leading coefficients. When I have a negative leading coefficient, that changes the end behavior of the graph to be the opposite of what it was when it was a positive leading coefficient for the same power, in this case being odd. Now, when I have that leading coefficient being negative, and I'm talking about even powers, we're looking at a reflection, across the x-axis, and this is a reflection across the x-axis. So just flip the graph across the axis. So keep that in mind as we're going. So now we're going to apply the polynomial theory, which, graph the polynomial window showing its extrema in zeros in its end behavior. Describe the end behavior using limits. Now, I'm going to graph this so you can see it in the window, or you can graph it. But now keep in mind, I got A and B here, and for some reason I rewrote B, so I apologize for that, but we'll take care of that in a second. But graph the polynomial in a window showing its extrema in zeros in its end behavior. Okay, describe the end behavior using limits. So I'm just going to describe the end behavior. I'm not going to find the maxima and minima. We can. And I'm not going to be finding the zeros here. And we can do that too with the graphing calculator. And if you're not comfortable with that, doing that with the graphing calculator, you should be talking to me about it, because it's going to be one of those necessary things. Because although we're going to be able to factor a lot of things. Being able to find the zeros is going to be a necessity for you on the graphing calculator. But I'm going to expect you to be able to follow that up with work showing factoring. You need to know your factoring, period. Okay, so keep that in mind as we're going through this section. Now for x cubed plus 2x squared minus 11x minus 12, the max possible, there's two extremas and 3 zeros as I look at that graph for A. Okay, I've got 2 extrema and 3 zeros here. And it's crossing the axis here at 1, 2, 3, 4, at 5, -5, -1, and 3. Okay. And as the limit of f of x approaches infinity, it goes to infinity. And as the limit as f of x, should be f of x here, somebody got lazy, but that should be an f of x. The limit of f of x, let's put that in there for those folks that are not having any video on this. This should be of f of x, and I'm sorry for missing that. Now, as x approaches infinity, is negative infinity. Well, that makes sense as it goes through as we look at this graph. And I'm very confident you can find the relative max, the relative min, as we go through these and look at these graphs. Now, in g of x, 2x to the fourth plus 2x cubed minus 22x squared minus 18x plus 35. Sorry about that. Just kind of bleeped out. Let's get these back. Now, in this next one, we're talking about 3 extrema, max possible on this, and 4 zeros for a quadratic. Now, the limit of g of x as x approaches infinity, well, hey, look, as x approaches infinity, it's going to positive infinity. The limit of g of x as x approaches negative infinity is negative infinity. So that's what we're looking at. Again, confident you can find the relative max, relative mins of this function as we're going, and this is an absolute minimum, by the way, in this function since everything goes up. So, just keep in mind what those are and be able to find your zeros using your calculator buttons. Now, moving on. Zeros of polynomial functions. Now, we're finding the zeros of polynomial functions. Find the zeros of f of x equals x cubed minus x squared minus 6x. Keep in mind, you're expected to be able to factor. So I'm going to factor out an x, and I'm going to set this equal to 0 as we go. So I'm going to factor out the x. So the idea of zero product rule comes in. Either, after I factor this out, I've got x squared minus x minus 6, and I've got x minus 3 and x plus 2. I'm just going to double check to make sure that that's right. Yep. And these are zeros, and that should be a 0 as well. So let's put that in as 0. And when is x 0? For what value of x does it make this 0? It's 0. And this is 3, and this is -2. You've done that before, but that's why we do it. But those are the spots on the axis that the graph will cross. Now I can find them. I got my -2, I got 0, I got 3. Okay, so we can look at it on the graph, but we got to be able to show algebraically. And notice the steps. I just don't jump here because I copied something out of Slater or something, or I just looked at my graph. I show my work, the presentation of your solution. Okay, a reminder, repeated zeros are known to be zeros of multiplicity. Okay, multiplicity of a zero of a polynomial function. If f is a polynomial and the quantity x minus c raised to the m power is a factor of f, but the quantity x minus c raised to the m plus 1 is not, then c is a zero of multiplicity m. Okay, that's that multiplicity m of f. Moreover, multiplicity explains the behavior of the function at the zeros. If the polynomial function f has a real zero c of odd multiplicity, remember odd would have to cross the graph. Then the graph of f crosses the x-axis at c 0. Remember, that's a 0, and it crosses there. And the value of f changes sign at x equals c. Now, if a polynomial function f has a real zero c of even multiplicity, 2, 4, 6, 8, then the graph of f does not cross the x-axis at c, 0. And the value of f does not change sign at x equals c, because it will still be positive or still be negative. Up here, it'll change from positive to negative or negative to positive. So touches or bounces on the x-axis is even powers. Real zeros, even multiplicity, does not cross the x-axis. Function does not change the sign. Okay, it's either all, at that point it touches the graph, and at the point of touching the axis, it's 0 at that vertex of that spot. And I use that loosely. And then when we're talking about real zero of c, of odd multiplicity crosses the x-axis at c0, then the function changes sign at x equals c, and that's for the odd powers. So the green's odd, the blue's even, and that's what we're going on. Now, if you put this graph into your calculator, you'll come up with something that looks like this. But let's talk about this graph before as you're doing that. This is a cubic, okay? It's going to cross the x-axis at -2, okay? This is a parabola, okay? It's going to cross, or touch, I should say, the x-axis at 1. How did I know that? This behavior is going to be cubic. This behavior is going to be parabola, okay? So as we're looking at this, we're talking about x minus 2 coming up here, and it looks cubic. And this one, at x equal 1, it looks like a squaring function. And I say square, but squaring function. But this is to the 5th degree. Okay, the zeros are x -2 with multiplicity 3. The multiplicity's up here because it's going to be 3 -2's. Crosses the x-axis. Now, x equal 1. Multiplicity 2 does not cross. It bounces. I expect your answers to look like this in your assignments and your test. Okay, the y-intercept. I'm finding the y-intercept. When is this 0? Okay, so I've got this when x is 0. What's the y value? Put in 0, and I've got 8, and I've got this as -1 squared. Okay, so it's 1. So in this 2 cubed, that's where 8 came from. 8 times 1 is 8. So at 0, 8, I'm going to cross the y-axis. So that's my y-intercept. My limits. As x approaches -infinity, my value is going to go to -infinity. As x approaches positive infinity, goes to infinity. And that's my end behavior values. That's what I'm doing here. Okay, these are the things you need to make sure. These are the basic things you need to make sure you have on. If you're just giving me like the zeros and then you're not doing anything else, you're getting half points on your assignments. That's all there is to it. Make sure you're complete. Now, the intermediate value theorem explains that a sign change applies to real zero. If a and b are real numbers, then a is less than b. Okay, so a comes first in the number line, and b is second. And if f is continuous on the interval from a to b, so x is continuous on this interval, then f takes on every value between f of a and f of b. Okay? In other words, if y naught is between f of a and f of b, so I've got a y naught in between here, this value of f of c, so I've got f of c somewhere in here they're talking about, for some number c in this range from a to b. In particular, if f of a and f of b have opposite signs, so if this is negative and this is positive, one is negative and the other is positive, then f of c is 0. Okay? For some number c, so there is a 0 here. And this is, by the way, what your calculator looks like when it when it searches for your zeros on the x-axis. It looks for this change, okay, as it's going through. So it's an interesting thing. But if f of a is less than 0 and f of b is greater than 0, then there's f of c, which is 0. And that's what they're talking about, and that's the intermediate value theorem. Now, using the intermediate value theorem, explain why a polynomial function of odd degree has at least one real 0. Well, it's got at least one real 0 because it's going to cross the axis, because it's odd. Okay, polynomials of odd degree have opposite end behaviors. So let f of x be an odd degree function. So the limit of f of x as x approaches -infinity. So this is the opposite of this is equal to the limit of f of x as x approaches infinity. So I'm just saying that these are equal when I take the opposite of this. In order for the function to exhibit this opposite end behavior, it must cross the x-axis at least once, supporting the idea of at least one real zero. Now, zooming to uncover hidden behavior. Now, not zooming out, I'm talking about zooming in. Okay, so put this function into your calculator here. Okay, and make sure when you do it, you're very careful about putting everything in correctly, because if you don't, it's not going to look the same. Now, suspect the graph to cross 4 times with 3 extrema because it's to the 4th power. Okay, then place graph in calculator, search for zeros and extrema as we go through it. After you get in your calculator, okay, make sure you got all your plots and everything off. Your other stuff, this should be the only one on. Hit your graph, and we'll see what I've got here for graphing. We're going to go to zoom standard. We'll get a 6, and we'll graph that puppy. Okay. Now on this one, it looks like it comes across. It goes ways down here, and it goes up. It looks like it comes across, or it kisses coming through here. So I'm going to zoom in here, and we're going to find out what's going on with this. So I'm going to zoom in. I'm going to do a 2. And I want to zoom in on this area. I'm just going to move it over a little bit. Okay, so we should zoom in on this area here and enter. Okay, it doesn't like me much. But let's see what's going on. And notice what's going on here. Instead of a kiss, it actually crosses this axis. So we're going to zoom in again. And this is kind of nice that I don't have to use the zoom box, but we'll wait for it to catch up so I don't have a funky thing, because I want to make sure you have it where we're supposed to do it. So although it looks like a kiss on that initial window, like it's just going to bounce back and around that number, it really isn't. It actually crossed, and we have I can actually find the zeros here and here. If I actually go to second calculate, and I'm going to find my zeros now and enter. Remember, zero findings from left to right on either side of the zero. So that's my first zero at 1.133. So I got my first zero at 1.133. And let's go find my second zero there. And that's just on the inside of that function. I'd have to find the other ones the same way in a like manner as we're getting going. But we're going to go here. And now remember, the zero is all about the change in the sign. So I could do one right here. As long as I'm above the axis on this right side, it doesn't matter how far above the axis, I don't think. Well, okay. We'll see. You see that? And I've got that. It's going to give me a 0 value because of the sign change. And this is 1.36. 7. Okay, as I round, remember the 3 digits? As I go through, so we're finding all of the real zeros on this, and I'm getting that done. So I've got those going on, and let's zoom out now and get those other ones. I'm going to zoom back out. We're going to go 3, and we're going to go over and enter. Okay, now we're going to get this other 0 as we go. Second calc, 0. Remember, from the left, then to the right. So we got another 0 here at 0.5. And we got our last 0, remember, we got to zoom out again. And we'll go back to second, that zoom format, we're going to go out, we're going to do 3, and we're going to move the cursor over a little bit, and we're going to zoom out, hit enter. And we got our last 0 here, so we're going to do that. Do a 0. It might take us a while to get back to that part of the graph. Whoops, a little bit far. Second calc, find my 0. That's my first one. My right bound is here. And it's that change of sign that they're testing. So it's -3.1 after I round. So my zeros of this, if I'm talking about my x, my x value is -3.1, that's rounded, and 0.5, 1.13, and 1.369. Excuse me, 7. And just to make sure you guys got your graph, I'm going to zoom out again to get my graph. Back in here, I've got a... Okay, so that's our graph, and I'm sorry for the bummer about the video and the interruptions. And these are our zeros of that graph: -3.1, 0.5, 1.133, and 1.367. And I was able to see those when I zoomed in. So keep in mind, you got to use that zoom key a lot. Okay, well, that's going to be notes for today. I hope things are going well, and we'll talk to you guys soon.